Here we have the infinite series of 5n plus 4 dividing by n times 2 to the n, and we want to use the limit comparison test to show that this series right here converges. And to use the limit comparison test, we call the given series here, we call it the series A sub n. We need to come up with a B sub n, and then we have to show two things. We have to show that the limit of A sub n divided by B sub n as n approaches infinity is equal to a real finite positive number. And then we have to show that the B sub n converges. Then we can say that the given series converges. And so right here we will let A sub n be the given sequence right here. And then we just let B sub n be something similar. So here we can just let B sub n be this. Just drop the 4. And then next we need to show that the limit of A sub n divided by B sub n is equal to a real positive finite number. And so we need to show that the limit of A sub n dividing by B sub n and then the difference here is just the 4. And so we can record it if we're dividing by a fraction, so we're dividing by this quotient right here, then it's the same thing as multiplying by the reciprocal. And the n times 2 to the n right here, that will cancel out, and so this and this, they will drop out. And then what's left is just the 5n plus 4 divided by 5n. And if we allow n to run to infinity, then we can, right here, we can use L'Hopital's rule. But this one is simple enough. We can just divide the top and the bottom by 5n. So we just divide everything on the top by 5n and everything on the bottom by 5n. But otherwise, we can just use L'Hopital's rule and it'll be, it will come out the same. So this would be 1. And then 5n divided by 5n is 1. And then we have 4 dividing by 5n. And as n approaches infinity, 4 divided by 5n approaches 0. So we get 1 plus 0, which is 1. And then here's 1, so we get 1. And so we have shown that the limit of A sub n over B sub n is equal to 1, which is greater than 0. Because if it's equal to 0, then we have to use another test. So we have shown the first part. We've shown that the limit of A sub n divided by B sub n is equal to a positive finite number. And so the objective here is to show this series converges. And so we have to do one more step. We have to show that the B sub n converges also. So we need to show that the B sub n, which is this one, B sub n is without the, this is B sub n. So we need to show that this series here converges also. And so we can see that this one, the n here will drop out. And then this is a constant phi, so we can move it and place it in front of the summation sign. And then the 1 over 2 to the n, this is the same as 1/2 to the n. And this right here, this is a geometric series with common ratio. R equal to 1/2. And so series converges. By geometric series test. Recall that the geometric series test says that if we have a geometric series with common ratio between -1 and 1, then the series converges. And so we have shown two things. We have shown that the limit of a sub n divided by b sub n is equal to 1, which is a positive number greater than 0. And then we have also shown that the series b sub n converges, and therefore by the limit comparison test, this series right here, by limit comparison test. And so that's how the limit comparison test works. First, we have to come up with a series b sub n, and then we have to show that the limit of a sub n over b sub n is equal to a positive finite number. That's the first thing. And then the second thing is we have to show that b sub n converges. And then we can say that the series a sub n, or the given series, converges.